Hello, my name is Jimmy Gawron. I'm currently a junior in the AOSS department, and for the past 10 weeks I've been working with Dr. Nilton Reno on the optimization of the U of M miniature electric field sensor. Currently we are studying the formation of terrestrial dust devils in order to verify a more accurate model, a simulation model created by Dr. Reno. We will then take this model and use it to study the formation of dust devils on Mars to determine the contribution that the dust devils have on the composition of the atmosphere there. Now, one of the most important parameters in dust devil formation that we are studying is the effect of electric fields on dust lifting. And in order to measure the electric field during the formation of a dust devil, we were able to create a new and innovative electric field sensor called the U of M Miniature Electric Field Sensor. And it has the capability of measuring the ambient electric field as close as 2 centimeters from a surface at an accuracy of 10%, even in the presence of being bombarded by dust particles. Now this is the current design of the end cap, and some disadvantages of this current design was that in order to turn the sensor on or off or to recharge the battery, the sensor had to be disconnected from the end cap and the wires manually disengaged on the inside. And this was very time-consuming and difficult while working with it in the field. This is what I was able to design the end cap to optimize the design. And some of the features of this design was that it incorporates a slide switch to turn the sensor on and off, as well as an exterior charging port. Also, the snap fit of the old design was replaced by a screw hold for more stability. Here's the assembly model for the design. The translucent portion is actually the newly designed end cap, and you can see the interface between the end cap and the slide switch, as well as the charging port. Now let's go to the physical model that I brought today. And you can see this portion is the newly designed end cap. Here's the slide switch to go off and on, as well as the exterior charging port. And finally, the screw hold creates very good stability between the end cap and the sensor, which ends up turning and senses the electric field and sends the data out through a radio frequency wirelessly to a computer that takes and holds the data. Okay. The next step in redesigning the sensor was to make it space qualified for use on a satellite. And the first and major redesigning step was to replace the old motor with a new space qualified motor. And some of the characteristics that we were looking for in choosing a new motor was that the materials that the motor be made out of were space qualified so that it would not outgas in the presence of a vacuum. Also, we were looking for the correct power requirements of the electric motor to run our sensor. I was able to take this new and larger sensor and incorporate it into the design of the electric field sensor and actually put the electric motor inside the sensing cylinder as well as the drivetrain, and through a series of bearings turn the outside sensing cylinder, which then reads the electric field and records that data. The final step in the design process was to subject the geometric model to a vibrational analysis. We wanted to make sure that the structural integrity of the model would be able to be maintained even in the presence of the vibration environment of the liftoff of a Delta II rocket. I'm using the MD Nastran software in order to do this analysis, and here's a picture of the geometric mesh that I'll be using to do the analysis and kind of see how the model will react to the different forces. And that is my presentation for today. Thank you for your time.